Okay, so I'm Dan Dicken. I'm working in Paris, ESAC, and I'm part of the MIRI test team, so I spend a lot of time looking at MIRI test images. So I hope to convince you that these are pretty cool detectors, literally. So we're going to be operating at 5 Kelvin, not 30 Kelvin, so much colder, and that's why our detectors are different from the near-infrared ones. So start with a quick summary of where the detectors come from. So they were made in California by Raytheon Vision Systems. They're million-pixel arrays, so slightly smaller than, half the size of the near-infrared ones. They're arsenic-doped silicon arrays with 25 micron pixel pitch. Arrays of this type, similar to this, were flown in Spitzer, WISE, MSX, and Akari, so we are familiar with this technology before. But they're most closely related to the detectors that were on IRAC, and the IRAC's detectors were a quarter of the size, so 4 times bigger. The main differences are we have 16 times the amount of pixels, we have smaller pixels than IRAC, we also have reference pixels, which I'll talk about later. But I think the most important thing is there was 10 years extra manufacturing experience between the manufacturer of the two detectors. So I think basically they just got a little bit better at making them, so hopefully we'll see much better results. So an overview of the performance. The performance of the detectors are published in a series of BASP papers that are referenced at the end of the talk. So MIRI has 3 detectors, 1 for the imager, and then 2 for each arm of the MRS, which is the medium resolution spectrometer. So it's got a shortwave arm and a longwave arm. We've got full redundancy in the electronics and the temperature control, so a side A and a side B. As you see in the table here, there's actually there's 2 columns here because we've got 2 slightly different types of detector. For the shortwave arm of the MRS, we traded slightly lower absorption efficiency to reduce the dark current. So you'll see that here. It's the dark current difference between. Otherwise, they're basically identical detectors. There's just a difference in there's a difference in the reflective coating of the other 2 detectors as well. But they're basically all 3 almost identical. There's a good uniform response on the detectors, so this is no more than 3% RMS. And we've got a very small proportion of inoperative pixels, so that's either dead or hot pixels, so it's less than 0.1%. And unlike the near-infrared, we can go all the way out to 28.22 microns. So there's interesting stuff out there that we want to see. So we've got usable range right out there. You just saw an image from Marco, the same sort of picture, but I thought I'd show it again just to get your heads around this idea of frames and integrations. So each one of these orange dots is an individual frame. So MIRI has frames just like the near-infrared instruments. An integration is a group of non-destructive readouts, and then you can have several, so then that makes a ramp. So that's one integration, then you could have several integrations, that's an exposure. But what MIRI doesn't have is groups, so we never average together frames, and that's basically because we don't have the same data rate as the near-infrared instruments. So everything that the telescope sees comes down, so that gives us much more opportunity to do the best kind of calibration that we can. Little MIRI fact for you here, just for interest. It's actually possible to do 65,535 frames per integration, and the same number, 65,535 integrations. So the longest possible exposure you could do with MIRI is 8,525 years. But unfortunately, the mission configuration is only 3,352 years. But I think SDSCI are going to limit you to about 3 hours per exposure, unfortunately. So if you're thinking of doing these really long ones. But it would be possible if someone goes up and refuels a telescope in the future. Just bear that in mind. Yes?
For the question, maybe Mark answered it, but what's the difference between a sequence of integrations and one exposure with lots of integrations and the same number of exposures each with one integration? Why would you choose one versus the other?
I will go on to that, but basically for us, it's the timing between integrations is very well known, and the timing between the exposures isn't. And so it's much better, it's a much more efficient way of doing it, so it's easier to calibrate. Yeah. So to give you an actual image from the instrument and sort of explain in images what I was just showing in those plots, there's quite a lot going on here, so I'll try and explain everything to make it make sense. So what you have here on the left, this is actually an image of one frame. So this is one complete readout of the MIRI detector. So if you looked at the level 1 data, this is what you would get. And what you see here is, you see the mask, because this is the imager, so you see the Leo mask here for the coronagraph, and these are the 4-quadrant phase mask here. You can also see the slit for the LRS, and then this is the imager field of view. And then at the top of the image here, so this, if you actually looked at level 1, you'd see these kind of 4 extra images on top. And that's the reference output images that we have from MIRI. So we have separate reference pixels that are read by a different amplifier, and they are outputted just for efficiency in this format at the top. But what you're more likely to see is actually this image. So this is an image of 100 of these frames put together. So this is now a slope image. So the units of this image are in dn, so data units, and this is the slope, so it's dn per second. And you can see, obviously the fidelity is much better. And what we've got here is a zoom in to the side of the detector here, and you can just see this line of pixels, and those are reference pixels, which are different from the reference output image, so they're read. There's actually just one column of reference pixels on each side, and they're read by the 4 amplifiers. You get column of 4 reference pixels, so we have 2 references there. So yeah, MIRI has 4 amplifiers, same as the near infrared, but we have their 5th amplifier, which reads out this reference output image. As I was just saying, there's actually no dead time between frames, so the integrator simulates an integer of the frame time. And so the timing between exposures is not controlled, so that's dependent on the latency in the ICDH system. So it's really the best timing observations you can get by taking many integrations within one exposure. But you're limited in exposure time because you will have to dither to avoid cosmics, dead pixels, that sort of thing. So you can't just sit in one position. MIRI has subarrays as well. The hardware can actually produce any subarray you want, but we've limited that to 9 predefined subarrays. And if you look here, some of them are obvious. Some of the subarrays here are where the coronographic 4-quadrant phase mask and the Leo mask is. This is the slitless subarray here. But also these subarrays are for bright skies. So with a subarray, basically because you're reading less of the detector, you can do it a lot quicker. And if you can do it a lot quicker, you can look at something a lot brighter. So this is what this subarray here is, the bright scale. If you're looking at the sky, if you look at something very bright, you can use that subarray. But subarray times don't scale linearly. You can't just half the size of the detector and you get half the time to read it. There are overheads associated with that, but all of these things are predefined, and you'll see those in the APT. Just to say, for subarrays such as the bright sky, you're only going to get to use those as it's absolutely necessary in your science, because it does somewhat disturb the array, moving from subarray to full array and back again. But obviously they'll be mandatory for things like the coronagraphs. You'll have to use subarrays for those. We also have what's called fast and slow mode in MIRI. So fast mode is sort of the normal mode for the imager. So the difference between them is just how many times you read the pixel. So for a fast mode sample, it just samples a pixel once during a single clock cycle. And in slow mode, it will sample that many times. Again, the electronics will allow us to do that in any kind of order we want, but we've got a predefined order, which is 8 samples for the slow mode here. So you get a 24-second frame. And for the fast mode, you just have the 1 pixel time, which takes 2.8 seconds per frame. So fast mode will be the default for the imager, and slow mode is going to be the default for the MOS, because we predict slightly lower noise and a slight signal to noise gain for noise limited observations. So about performance and testing, we've done a lot of tests with the detector. Most recently with the flight detectors was at Goddard Space Flight Center. I think you'll hear a lot about this test over these 3 tests that we did there over the next couple of days. So this is the instruments inside the test chamber there at Goddard. But additionally, the MIRI team, we test flight spare detectors with flight clone electronics at NASA JPL. So there's a lot of expertise there, so we do a lot of extra tests on the performance of these detectors, because when you're operating at 5 Kelvin, physics gets a bit funky, so there's a lot of things we can look at and a lot of things we can learn about the detectors before flight. But so far, the MIRI detectors have met all of their requirements and also surpassed them in a lot of ways. For example, we have a requirement for 100,000 electrons in the well depth, but we can actually integrate to well over 90% of that ramp to saturation. and our measured well depth is actually approximately 250, so we can look at brighter objects for longer integration times. So this is all good stuff. But we have non-ideal behaviors, like the near-infrared has non-ideal behaviors. We've got some new ones. So basically these non-ideal behaviors are well known in these types of detectors from things like IRAC in the past, but we have some new ones that IRAC and the other detectors in WISE didn't have, and we've lost some as well. So the new one is the last frame effect. So what you'll see here is this last frame at the end of the ramp just drops. And the reason for that is we reset by row pair, and the adjacent row pair seems to affect the last frame of the previous row that was reset, and that just pulls this frame down. But we can either reject that, or we're coming up with a correction for that one. What we don't have is droop, which I think people that work with Spitzer will have heard of that, and that was sort of an extra component that was proportional to the signal, but we don't see that in our detectors. As I said before, what we get that Spitzer didn't have is we get to see the whole of the ramp. If you're working with Spitzer data, something like MIT, all of this information here would have been averaged and sent down from the telescope. So that gives us a big opportunity to calibrate better than Spitzer was able to. The last thing on this slide is the column and row pull up and pull down. And there's an image here from some of the testing we did at JPL. And you see for bright objects, you get this effect of pull up and pull down. But we've got a model developed for that, and hopefully we'll be able to remove that in flight. And that's really only for the brightest objects.
About 3 minutes now.
Okay, perfect. Something that I work a lot on is memory effects. And Marco also mentioned this, that we do have persistence, which a lot of you might know as latence. It's also called latence. We've done a lot of tests for this. For the most part, persistence shouldn't affect observations. It's usually a few minutes after your observations. It's less than 0.5% of your original signal. And here's an example of some latent images. And actually, on my screen, you can see them, but you can't hear, which is even better. So what we have here is an actual test from JPL. And this is the illuminated image of 5 minutes integration time. And then this is the dark image taken 90 seconds after. And I don't know if anyone can make that out, but you can actually see there's this is a log scale image. So you can see there's a latent here, and then this one's taken 5 minutes after, and this one's taken 5 minutes after that. So you can see it's a very smaller effect. And also, if you imagine you have backgrounds within MIRI, that somewhat drowns out that effect, so you needn't be too worried about it. So that's latence. We also have imprints. So this is something we saw with IRAC as well. So that's if you put something really bright on the detector, that puts an imprint, and that's something that doesn't change in time. So it's something that we think we can only get rid of by annealing, and annealing is warming up the detector, basically heating it up and cleaning it completely. The other memory effects we see are drifts, so signal drifts. So if you look at the same thing over and over again, you'll see that the response you get increases with time. And what we actually think is the latence and the drifts are related. So it's all to do with traps within the detector. So sometimes you're filling traps, so you're losing some of your signal, and sometimes the traps are emptying, so that some of your signal's coming out. So we're working a lot to understand that and working out which kind of observations will be affected by that. But these are common to these kind of detectors, so it's not something new. And hopefully, as I'll show you in the next slide, best practice should avoid a lot of these problems for most types of observations. So there are several things you can do that we're going to be common to use for MIRI. The first thing, of course, is dithering. So you're never going to stare in the one place apart from the exoplanet people and other time series observations. You're never just going to sit in one place. You're going to move around the detector. So obviously, the longer you stay in one place looking at the object, the stronger your latent image is going to be in the next image. So you're going to move around. So that somewhat mitigates these memory effects. Also, as you've heard, there are overheads with the JWST observatory. It's going to take time. It's a big observatory. It's going to take time to slew across the sky. In that time, these persistent things decay. They're not a function of reset. It's just a function of time. So in the overheads, you're going to lose quite a lot of that signal as well. And as I mentioned before, MIRI backgrounds are high, so that dilutes somewhat some of the more subtle effects that you get from persistence in the images. We also have a pipeline that we're developing for MIRI to correct some of these effects, and at the moment it corrects the following effects: the bad pixels, obviously, non-linearity, reset switch charge decay, cosmic rays, persistence, and then the last frame effect. But we're still working on that, and we'll develop that throughout the mission. This is just another MIRI fact, just to bear in mind that MIRI backgrounds will be high. They're not the same as the near-infrared backgrounds. If you're looking at 25 microns, your integration time is limited by the background itself because it's so bright. So you'll only be able to integrate for 45 seconds before you have to reset and then take another run. And then for reference, these are some of the fluxes that we're expecting at the different wavelengths that you can refer to in the slides later. So in conclusion, MIRI meets all its requirements. It exceeds them in terms of detectors. Most known non-ideal behaviors are well characterized and should be mitigated, corrected. And I think I can speak for the whole of the test team today that we're quite optimistic about the performance of the mid-infrared detectors on JWST. And that's a lot. Thanks.